So here's our problem. In the city, with a lot of one-way streets, you can only travel north or east. And they've given us a little map here where the streets are laid out in these grids. Determine the number of routes from A to B. Now, this is what I'm calling a sort of a pathway problem, because we're trying to figure out the number of paths from one point to another. Questions like this are sometimes also given to you using sort of patterns of letters, and you're supposed to figure out the number of ways that you can spell a certain word, or a number of ways you can use this pattern of letters to spell a certain word. Okay? The approach that you take to a problem like this is related closely to Pascal's triangle. If we're interested in going from A to B, we start at A here, and we're going to look at all of these little intersections. So if I go to the next set of intersections here, okay, if I start at A, there is one way that I can get to that intersection there, and one way that I can get to that intersection there. If I now consider sort of the next set of intersections, here, here, and here, well, there's one way that I can get to this one here. I can go here and then here. There's one way I can get to this one up here. I can go here and here. But there are two ways that I can get to this one. I can go from A up to here and then like that, and then, or A across and then up like that. If I go now to the next set of intersections, these ones that I'm putting in green here, up here, there's only one way I can get to that point, just go like this. But this next one, on a diagonal, there are three ways that I can get to it. I could get to this point one way, and then there's one way to there. There were two ways I could get to here, so there's another two ways that I could get to point 3. Same thing with this one here, 3 and 1. So you should be starting to see a little pattern here. These are kind of like the terms in a row of Pascal's triangle. And we get each term here by adding sort of the two numbers above it, or that come before it in the pattern. So if we continue this pattern, right here at this intersection, we're going to have a 4 from the 1 and the 3. We're going to have a 6 from the 3 and the 3. And we're going to have a 4 here. The next 2 points, we're going to have a 10 and a 10. And at point C here, we have 20. So there are 20 ways that we can get to point C. And then the pattern continues again. Our next 2 points, we're going to have 20 ways that you can get to each of these, because there are 20 ways to C. And then if we're looking at this point right here, there's only one way from there to there. So 20 points. Again, 20 ways to get to there, 40 here, 20 plus 20, and then 20 up here. Our second last row here, we've got 60 and 60. And then finally, at point B, we've got 60 plus 60, or 120. So there are 120 different routes from A to B. Now, is there another way that you could do this without sort of drawing out Pascal's triangle? Well, let's just draw a line here and think about it. In order to get from A to B, well, let's just think about how we can get from, first let's think about how we can get from A to C. So just going from A to C. If we're going from A to C, we need to go north 3 times, okay? And then we have to go east 3 times. Okay? So we've got north, 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 east, east, east. Okay? Now we don't have to do them in that order. We could go north, east, north, east, east, north, north, etc., etc., etc. So the question then is, how many ways can we arrange these 6 elements here? Well, we have 6 elements to arrange, and we have 3 n's and 3 e's. So the number of possible arrangements is going to be 6 factorial divided by 3 factorial, 3 factorial, okay, from our discussion on permutations back in Unit 1. What happens as we go from C to B? We'll do this in red over here, so C to B. Well, to go from C to B, we have to go north twice and east twice, and we can do those in any order that we want. So that's 4 things, 4 factorial, and then divide out the indistinguishable elements. 2 factorial divided by 2 factorial. And because this is a two-stage process, we are going to multiply the number of possibilities that we have for each of our 2 stages. So we can work out what each of these things are. We can get, well, let's see, 6 factorial divided by 3 factorial is going to be 6 times 5 times 4. And canceling out one of these 3 factorials like this. And then on the bottom, we're going to have a 3 factorial, which is just 6. Then over here, we can cancel out one of our 2 factorials by just changing this to 4 times 3. Take out the times 2 times 1, divided by 2, because that's 2 factorial. And we end up with, let's see, 6 times 5 times 4 divided by 6 is just 20. 4 times 3 is 12, divided by 2 is 6. So again, we get 120 different roots. The other way to think about it is to look closely at what formulas we have right here. Okay? We've got 6 factorial divided by 3 factorial divided by 3 factorial. We can rewrite this as 6 factorial divided by 6 minus 3 factorial, 3 factorial. And we can write our second term as 4 factorial divided by 4 minus 2 factorial, 2 factorial. These 2 expressions can be written as combinations. This one is 6 choose 3. This one is 4 choose 2. So we can think of it in terms of combinations or in permutations, or we can think of it as something kind of like Pascal's triangle when we're figuring out the combinations.